Here we're going to talk about the Fischer esterification. Fischer esterification is definitely one of our oldest reactions that we study in an introductory organic chemistry course. Now, the Fischer esterification, sometimes referred to as the Fischer-Spear esterification. Fairly old. It was initially published all the way back in 1895. If you're interested, you can find that paper from Emil Fischer and Spear, Arthur Spear, at this reference. And that's again 1895, 22, and page 3252. So even while it's a very, very old and reaction, still extremely useful for synthesizing esters. And specifically, it makes esters from a carboxylic acid and an alcohol. And when you combine those in the presence of an acid catalyst, you form a new ester with water as your byproduct. So we'll take a look at the mechanism of this reaction. And we'll start with just looking at a relatively simple example. And that's the reaction of acetic acid with ethanol. Now, if you've learned about acyl substitution reactions, you know that by themselves, carboxylic acid and alcohol probably aren't going to react. The carboxylic acid is not a great electrophile, and the alcohol, being neutral, is also not a terrific nucleophile. And so that's why, in general, for this reaction, we not only have to add an acid catalyst, but we very often need to heat it. Now, that doesn't completely solve our problem because, as we're going to see, there's significant equilibrium issues with this reaction. Another reaction that you'll learn about at some point is the hydrolysis of esters. And the hydrolysis of esters, if you do it under acidic conditions, happens under the exact same conditions. So that means we've got to pay a lot of attention to equilibrium in this reaction. But before we do that, we're going to look at our mechanism. And as with many reactions of carbonyls, where you have an acid catalyst, that acid catalyst is there to activate your carbonyl. So carbonyl gets protonated, and that's going to make it a better electrophile. And we need the better electrophile because our nucleophile here, an alcohol, pretty mediocre nucleophile. But with the activated carbonyl, it adds in. Giving us the type of tetrahedral intermediate that is very, very typical for a nucleophilic acyl substitution reaction. In the next step, we get a proton transfer that's going to set us up for our leaving group. We need that initial OH group to be able to leave. And so if we transfer a proton over there, we get a much better leaving group. At that point, our remaining OH can add its lone pair in. This kicks out our water, which is our leaving group. Leaving us just one step away from our product, which is then formed by loss of a proton to form an ester. And so that's our mechanism, and regardless of what combination of alcohol and carboxylic acid we use, the mechanism is going to look pretty much the same. Couple things that we want to point out, though. First of all, is if this reaction is really catalytic with acid, we should see both the use of the acid as well as that H plus being regenerated. And we can see in the very first step, we use an equivalent of the acid to activate the carbonyl, and in the very last step, we regenerate it. So we can see that the acid is catalytic. The major problem, though, with this reaction is the equilibrium. And unlike many other reactions which have a very obvious step to drive the equilibrium forward, either an acid-base step or a leaving group that is a really bad nucleophile or something like that, this reaction doesn't have anything like that. And in fact, this specific reaction, acetic acid plus ethanol, when you look up the equilibrium constant for this reaction, it's just above 3. So that tells us it favors the products, but not by very much. And in fact, if you were to go through the calculations using an ICE table, I've actually done that in one of the full lecture videos that's elsewhere on this channel. I'm not going to do it here, but you find that if you're starting with one equivalent of both the acid and the alcohol, you're only going to get about 65% conversion. So most commonly with the Fischer esterification, we take the alcohol because it's, in most cases, not always, but most cases, it's very, very simple alcohol. Things like methanol, ethanol, isopropanol, benzyl alcohol, and so on. And we use this as the solvent. Now, if you had a case where the alcohol is much more complicated, then you have to look at other things to drive the equilibrium forward. Typically, it's not uncommon to try and take advantage of the water as a byproduct and to remove that from the solution. But normally, we just use the alcohol as the solvent. And that means we might be using several hundred equivalents of the alcohol. And so that'll, by having a ton of extra starting material, that takes advantage of Le Chatelier's principle to push the entire equilibrium forward. We can see, many different examples of these types of reactions. Again, the R groups that are attached to both the carboxylic acid and the alcohol, in most cases, won't make a huge impact on this reaction. So here's two very, different. Here we've got benzoic acid and methanol. But the overall outcome is going to be the same. We're still going to form that new carbon-oxygen bond here, which gives us our ester. This reaction can also be done, you could do an intramolecular Fischer esterification. In that case, you'd form a cyclic ester or a lactone as your product. One final thing that we'll mention here about the Fischer esterification, one kind of neat application is the following. If you start with ethylene glycol, which is this diol, and to that you add terphthalic acid, given that both of these molecules have a carboxylic acid at both, or I should say the acid has carboxylic acids at both ends, the alcohol has alcohols at both ends, you can form a new ester here that would give us this product. But notice now on the right, you still have a carboxylic acid. That could add another molecule of ethylene glycol. As well as on the left, we've got another alcohol, which could then add another molecule of the carboxylic acid. And so this is a linear polymer that's going to form. In fact, what we've made here, after you put enough of these together, this is how you make Dacron. And Dacron is a polymer that's used as a synthetic fiber, among other things.